By now we have learned how to generate expressions for hybrid orbitals by using linear combinations of atomic orbitals that we get by direct solution of Schrodinger equation. Okay. So, as we said earlier, why is it that hybridization is taking place? So that the electron density is optimized to form the bonds. So, see, electron cloud is what we have. We do not have like rigid particles, right, and that is the beauty of the system. The electron cloud can deform and adapt to the requirement that it faces. Right now the requirement we are discussing is formation of bond. So, if say for example boron, it forms a trigonal complex, a trigonal compound with fluorine BF3. So, it has to react with 3 fluorine atoms, it has to form bonds with 3 fluorine atoms in order to satisfy its valency, right. You can actually go back to this very fundamental concept of valency, right. So, 3 bonds will be there, and these 3 bonds according to Gillespie and Nyholm VSEPR have to be at 120 degrees to each other. That is why the electron cloud sort of deforms itself because the situation demands and forms these new orbitals. You can think like that. Okay. Of course, this orbital is used to, the hybrid orbital is used to explain the situation. Okay. It is not as if they are the cause, they are the effect of the cause really is minimization of the repulsion among electron clouds. Okay. Let us not forget that. So, you can think of these electron clouds as shapeshifters, right. Remember, okay, I can only remember movies from long ago. So, Terminator, where this bad element from future could sort of take the form of anything, or remember Species, or many such movies are there. So, electrons are like shapeshifters and they can modify themselves according to the demand of the situation, right. And the demand we have discussed so far is formation of 2 bonds or 3 bonds. We had said that we will back calculate the angle between the bonds, but I had a second thought about that. We are going to do a calculation, but we will do it with sp3 hybrid orbitals. Let us get ahead. So, now I want to talk about sp3 hybrid orbitals. So, sp3 hybrid orbitals means 4 orbitals are there, 4 hybrid orbitals, that means they are required in formation of Ab4 kind of molecules, where A is a central atom, and they should form tetrahedra. Before doing anything else, I can say that the angle has to be 109 degrees, because this is a one good way of drawing a tetrahedron, right. Put a dot, well, first of all draw a box, and unfortunately this has got distorted. This is all the sides are square actually, okay. This is a cube, perfect cube, not cuboid. So, put dots on alternate vertices and then join those dots to the center, you have your tetrahedron. So, this is what we want. Since we want 4 hybrid orbitals, all the 3 p orbitals have to participate. And let us say, to start with, we have a situation in which all the 3 p orbitals make equal contribution to each of the hybrid orbitals, right. So, what should the coefficients be? So, before showing you the results, let me just work it out. So, our expression will be something like this: psi hybrid is equal to C1 psi 2s, and I want equal contribution from each of the p orbitals. So, I can write plus C2 psi 2px plus C2 psi 2py plus C2 psi 2pz. If you cannot read my handwriting, please do not worry, I will show you the final result in a nice form anyway. Okay. So, how many such hybrids are there? I can write 1, 4. So, here everything will be C1, is not it? and total contribution of 2s is 1 anyway. So, what we get is 4 C1 square is equal to 1. So, C1 is equal to half, simple, plus half or minus half, whatever, does not matter. For we can take either plus half or minus half, all that will change is your p orbital will look either like this or like this, nothing else will change. In fact, you will see a situation for coming very soon in which we are going to use a negative coefficient for psi 2s knowingly, okay, C1 equal to half, that is done. What about these C2s? Let me say something else. What will the C2s be? For one thing I can write right away, this hybrid orbitals have to be normalized, right. So, I can write C1 square plus 3 C2 square is equal to 1, and I know very well that C1 square is equal to 1/4 because C1 equal to half. So, I have 1/4 plus 3 C2 square is equal to 1. So, C2 square is equal to 3/4, well 3 C2 square equal to 3/4, C2 is equal to plus minus half. So, one solution is plus half, right. I can write plus half for everything, it is fine, okay. So, let us start with that, the totally symmetric answer in which every coefficient for the p orbital is plus half. So, the first wave function that we can write is and now before I say what the first wave function we can write, let me just clear all this and let us go back to the presentation mode, that is where things are written much more neatly. So, hopefully it will be easier for you to understand. Just give me a sec please. Alright, all set. This is the first one that we have already got. What will the second one be? See, your hybrid orbitals have to be orthogonal to each other, right. And again I will start writing, of course I will erase also later on. Suppose I write something like this, phi H2 sp3 equal to, this will be half, not much doubt about that, psi s. Now I will just write the orbitals first, psi 2 px, psi 2 py, psi 2 p, I have not written 2p there, but anyway psi 2 pz. Sorry for being a little inconsistent. Now, if I just multiply them and integrate over space, I am going to get 0. Okay. In any case, I know that mod of this coefficient, first of all I can write like this, plus C3 plus C3 plus, no, C3 plus, not a good idea to write C3 again if I write plus, C4 plus C5, and we know that mod C3 equal to mod C4 equal to mod C5 is equal to half, because every p orbital, that is what we are considering, every p orbital makes an equal contribution to the wave function. So, the squares must be add up to 1 and they are equal to each other. So, that is how. Okay, fine. So, now the mods are same, and what the other thing that I can do is I can take this integral phi h1 phi h2 is equal to 0, which means 1/4 plus C3 by 2 plus C4 by 2 plus C5 by 2 equal to 0. How did I get this? Because when I do the multiplication, remember integral of say psi 2s psi 2p x over all space is equal to 0, right, they are orthogonal to each other. So, that is how we have got it, and then they are normalized also. And then remembering that actually these are all plus half, well, plus or minus half, what it means is that I have to put in 2 minus signs for this quantity to be equal to 0. Understand what I mean? The C3 by 2, C4 by 2, C5 by 2, all mod of these, mod of C3 by 2, I can write like this, mod of C3 by 2 is equal to mod C4 by 2 equal to mod C5 by 2 is equal to half. Okay. So, what are the absolute values? Sorry, is equal to 1 by 2 into 2, I forgot that 2. So, is equal to 1 by 4. So, what I have here is that this is 1/4, this can be plus or minus 1/4, this can be plus or minus 1/4, this can be plus or minus 1/4. So, the only way in which this will be 0 is suppose I put in a minus sign here and a minus sign here, then I will get 0, right, 1/4 from here plus 1/4 from here, 1/4 from here, 1/4 from here, minus minus, that will be 0. And what I can do is in the next combination I can move this plus sign here, take the minus sign there. So, I can move the plus sign around. What it means is that for the coefficients of the p orbitals, 2 of the coefficients must be equal to minus half and one of the coefficients has to be equal to plus half. That is the only way in which the condition of orthogonality of the hybrid orbitals can be satisfied. So, there is no other way. So, what we have done is, remember, we have actually constructed these wave functions under a lot of constraints. We have made sure that contribution from each p orbital is exactly the same, and then we have required that they are normalized, and now we are required that they are mutually orthogonal also. So, that gives us leads us to the conclusion that 2 of the p orbitals must have coefficients of minus half, the third will have coefficient of plus half. So, first of all I can write like this, and then all I do is I just move this plus sign first. Could I have written plus sign here to start with? Yes, of course, how does it matter, right? Which one is H1, which one is H2 is in our hand, we will name accordingly. So, this is the complete set, orthonormal set of hybrid wave functions. Now, let us see whether the picture we have drawn is valid. Equal contributions from x, y and z. Can you see where x, y and z are here? Maybe I will draw again. This is a center, this is a phase center. So, join the phase center with this is a phase center, join with this x, y, and let us say this is the phase center. This is the easiest, most difficult to draw join the phase center like this. So, this is your x axis, this is y axis, this is z axis, let us say. Now, you can think of these hybrid orbitals as vectors, and you do not have to worry about psi s because it is non-directional anyway. So, what we are saying is that each of the axes x, y and z contributes equally to the length of the vector, right. We are taking squares, so plus or minus will not matter, we will only talk about length, not direction. So, where will this resultant vector lie? Actually, you can think of this smaller cube within cube. This is a cube, not a cuboid. Okay. Smaller cube within cube, the body diagonal of that smaller cube, that is your hybrid orbital. Okay. And equal contribution of x, y, z ensures that it is there. So, similarly you can see that the all the hybrid orbitals are actually along the body diagonals of the cube, and it is not very difficult from your solid state geometry to work out that the angle between body diagonals of a cube is indeed 109 point whatever degrees. Okay. So, we have 25% contribution from S, 75 contribution from P. More importantly, we have 25% contribution from each of the participating orbitals. made Vs, made Vp. Okay. We are going to discuss another situation shortly. Alright. So, remember there is no unique combination of solution. If you change the orientation, the coefficients will change. What will not change is the relative contribution. What will not change is the fact that they have to form an orthonormal set, complete orthonormal set. Now that being said, we have worked out the angle anyway. Now let us work out the angle in a little more formal manner, and to do that we will work with H1 and H2 orbitals. Okay. If you remember the formula, the working formula for dot product of two vectors, this is what it is. You take a dot product R1 dot R2, that gives you mod R1 mod R2, magnitude of R1 magnitude of R2 multiplied by cos theta. Okay. So what we can try to do is, what is the unknown here? The unknown is theta. What is the angle between H1 and H2? That we do not know. But knowing the vectors, we can find out the dot product, and we can also work out the magnitudes, the length mod R1 mod R2, and we can find their product. So we can try to find cos theta by dividing the dot product of R1 and R2 by the product of their magnitudes. To do that, first of all we royally ignore the s orbital. Okay. We have washed it out with a different color. We do not care about s anymore, well, for some time, because s is not directional, it does not count as a vector, it does not contribute in this discussion. So the vectors that we want to work with are x, y and z, px, py, pz, all equal magnitudes. Alright. So the dot product here would be what? Now remember this cos theta business. So cos theta of x and y is 0. This is well known in vector algebra, but I am saying this in case some of us forgotten. Dot product of x and y, y and z, z and x, all that is equal to 0. Dot product of x and x is 1. Okay. So what will I get? Half into half is 1/4. I can take 1/4 common. So I will be left with 1 minus 1, all that. So the first term comes from px dot px, 1 into minus 1. Second term comes from py dot py, plus 1 into minus 1. Third term comes from pz dot pz, that is plus 1 into plus 1. So what do I get? The dot product turns out to be, remember dot product is a scalar quantity, not a vector quantity. 1/4 multiplied by minus 1 plus 1, that is minus 1/4. We have worked out the dot product. What about the magnitudes? Magnitudes will be, well, these are at 90 degrees to each other, right, px, py, pz. So magnitude will simply be well, square root of half square plus half square plus half square. Yeah. So that will be root over 3 by 2. That is the length of the vector, okay, magnitude. So if I take product of magnitudes, then I get 3 by 4. So I have got the dot product to be minus 1/4, I have got the product of the magnitudes to be 3 by 4. What is cos theta? Cos theta is just the dot product divided by product of magnitudes, turns out to be minus 1/3. Take cos inverse of that, theta turns out to be 109.5 degrees. Okay. So we are convinced that this is an actual tetrahedron, okay, and everything falls together beautifully. It is a tetrahedron in order to minimize repulsion between bond pairs. But when we do that and we construct these hybrid orbitals, it turns out that we get the correct value of the angle. And this is going to be very useful, this kind of calculation, when in the next class we talk about non-equivalent hybrid orbitals. Okay. We will talk about water, wait for it. Okay. But let us finish this discussion. What happens if I hold it in a different orientation? I will not work out all of it, I will work out a part of it and I will ask you to work out the rest of it. What happens if H1 is oriented along z axis? Okay. And let us say I hold the other one in the zx plane. So I do not know whether this figure is very clear to you. This is what I mean. Why can I not draw a straight line? So, I am drawing on a screen. So, unfortunately I cannot, or maybe I can use a ruler, I do not have one, that is all. Okay, that is straight enough. This is z axis, this is x axis, y axis is pointing towards us, let us say. Now, I will, since I can change color, I will change color. What I am saying is, I will put H1 along your z axis, this is H1, and I will keep H2 in the zx plane. Well, this is x, this is z, sorry, I should have written that. So, it will be something like this, H2. You know, this is 109 degrees, 109.5 degrees, 90. So, 109.5 minus 90. Now, so where will H3 and H4 be? One will be above the plane towards us, let us say that is H3, the other will be below the plane away from us, H4, right. This is how we have held the molecule now. Now, we want to see what kind of coefficients we get, and we want to check whether it is compatible, whether it gives similar results compared to the earlier case where the coefficients were all either plus half or minus half. Great. So, how do I get the first one? First one is very similar, let me write a little bit. So, first one psi H1 let us say is equal to C1 into psi S. No, I will not write C1. Can you tell me what I will write? See, it does not matter how I hold it, contribution of S has to remain the same, right. We still want these sp3 orbitals. So, contribution has to be same everywhere and the total contribution has to be 1. So, without repeating the calculation that we have done already, I will write it is going to be 1/4. Is it going to be 1/4? C1, C1 square plus C1 square plus C1 square plus C1 square equal to 1. So, C1 square will be 1/4, C1 will be equal to half. So, the same coefficient that we got earlier will be there for the s orbital. But what about the p orbitals? Now, they will not be the same. See, for H1 I have held it along the z axis. So, only Pz will make a contribution, Px and Py will have 0 contribution. So, I can write like this 0 into Px plus 0 into psi Py plus what will I write? Let me write, what would it have been, C1, C2, C3, C4, C4 into psi Pz. Let me rewrite. Looks like I have written in indelible ink, cannot help it. So, psi H1 hybrid 1 is equal to half into psi 2s plus, again I wrote 2 anyway, it does not matter, plus 0 into psi 2px plus 0 into psi 2py plus something C4 into psi 2pz. Rest is simple, this is normalized. So, you will get 1/4 plus C4 square is equal to 1. So, C4 is equal to root over 3 divided by 2. So, already worked out one orbital, and what I see is that first of all the entire p contribution is from one orbital, that is Pz. However, if you take the square of coefficient of psi 2s and square of coefficient of psi 2pz, what do you get? 1/4 is to 3/4, that is 1:3. So, this is still an sp3 hybrid orbital, and that is what we are trying to emphasize here. If you hold the molecule in a different way, the coefficients will be different, but the overall picture does not change. Total S character, total P character will not change. What will change is contribution of individual p orbitals, does not matter. As long as the total S character and the total p character are not compromised, we are absolutely fine, because we do not even know which is x and which is y and which is z, right. We are, I thought this is indelible ink, now it is gone anyway. So, we are just writing things in a way to simplify problems. So, we are justified in simplifying the problem, that is what I am trying to say. It is okay if we hold the molecule in an orientation that makes our problem a little simple, as long as the overall picture does not get distorted. Okay. Now let us go ahead. So, this is what we had written, and in fact we have gone further than what is written here. We already know the values of C1 and C4, half and root 3 by 2. If you go to phi H2, then again C5 is going to be half. This is quite mundane now. What will C8 be? A very easy way of proceeding is by using the orthogonality of psi H1, mutual orthogonality of phi H1 and phi H2. So, what you get is 1/4 plus root 3 by 2 C8 is equal to 0. So, C8, hey, why did I write 1/4, sorry. No, what am I doing? I am multiplying phi H1 by phi H2. So, this is 1/4, this is also 1/4. So, 1/4 is actually correct, but it is root 3 by 2 into C here, everything is correct. Unnecessarily I had a panic attack. So, C8 is equal to minus 1/4 into 2 by root 3 is equal to minus 1 by actually root 6. Okay, is a minus fine? Actually it is, because it is on the other side. So, I mean it is towards minus z, so it is fine. Okay. What is the contribution of this pz orbital now? 1/6. Okay, whereas contribution is 1/4. So, 1/6 1/4, that is not sp3, that is because this C6 is non-zero. How do you find C6 now? Simple, 1/4 plus C6 square plus 1/6 is equal to 1 from normalization condition. And now since I have done so many and I have made a couple of mistakes also, I will not do all this arithmetic anymore, you do it yourself. I will erase. I will now just show you the final result and then I will go home. Okay, so you know how to get it, right, how to get the coefficients. This is how you get it, and the coefficient for Px here turns out to be root over 2 by 3. Now the thing is simple, the other two, once again the easiest way of starting the problem is to start with the mutual orthogonality with the orbital that has a maximum number of 0 coefficients, and then proceed, then you have fewer terms to handle to start with at least. But before going there, just have a look here. S contribution is half, 1/4. P contribution, what is it? Square of this 2/3 plus 1/4 of 3. So, just work it out, you will see that it comes to the same thing. You still have sp3 here. It is just that contribution from Px and Pz are no longer the same, because orientation is not symmetric anymore. So, symmetry actually has a very important role to play in handling quantum mechanical problems. We have this NPTEL course that we floated on symmetry some time ago. Lectures are all available. Whoever is interested, you are more than welcome to have a look at the lectures. If there are questions, I will be happy to answer them. Okay, so now the reason why tutorial problem is written here is that it is for you to do. Please work out the expressions for the third and the fourth hybrid orbitals, and I am showing you the result here. What I also want you to do is, I want you to work out the bond angles using the formula that we have discussed. This is something that I have done earlier. I do not know why you have written in bigger and smaller fonts, but the point is work out the bond angles and you will see that the bond angle once again comes out to be 109.5 degrees. So, once again we have a scenario where you have a regular tetrahedron we have worked with hybrid orbitals that are all equivalent to each other, same s character, same p character. And now I hope we have a little more quantitative idea of hybridization. There is only one thing left on the agenda as far as hybridization is concerned, and that is to discuss non-equivalent hybrid orbitals. That is what we will do in the next class.